afternoon, everyone. Welcome. So my name is Kaiming He, and I'm currently an associate professor in the ECS department. And I have been working on computer vision, deep learning, and AI for about 20 years. And I'm fortunate enough to see how deep learning AI has completely revolutionized computer vision. And then later, this trend has been propagated into many other sibling areas, such as language, robotics, speech, and then today, maybe it's propagating more to many other scientific areas. So in the next 10 minutes, I want to mainly convey two messages. First, some of the most successful generative AI models today were heavily inspired by some formulations from science and physics. And then in return, some of the most successful practice of Gen AI today can make significant influence to some scientific problems. So first, we have been talking about Gen AI, but mathematically or theoretically, so what is a generative model? Well, conceptually, a generative model is a model that maps from one distribution to another distribution. Let's say you have some noise distribution, you have some data distribution, and you train a neural network to connect these two distributions. Then, conceptually, you can sample from one distribution, and then you can map to another distribution by this magical neural network. So this is the mathematical formulation. And then this formulation and a solution to the generative modeling problem is heavily inspired by some physical models, let's say diffusion. So the diffusion process can be thought of as, let's say, you drop an ink into a bottle of water, and then after a while, the ink will diffuse inside the bottle. And then we can do the same on an image. We have an image, and then we gradually add noise, and then it becomes completely noise. And then if we describe this in the distribution space, it will turn data distribution into some noise distribution. So we can also formulate this problem as a probability flow. Let's say you have a data space, you have a noise space. Every single point here could be think of as the states in a very high dimensional space. And you can sample one thing from the data space, you can sample a noise in the noise space, and then you can connect them by a trajectory, let's say a straight line. So very simple. And then you can do this many, many times by just randomly sample things from these two distributions, and then conceptually you are building a velocity field. But this velocity field looks stochastic, it looks noisy. We can marginalize it. And if you do that, it provides us a way to connect every single data point to a point in the noise space. And then if we do that, we build a trajectory that can connect an image to a noise map. So conceptually very simple. But the question is, how can we solve this trajectory? So conceptually, this is an ordinary differential equation, or an ODE, in a very high dimensional space. And we want to find a solution represented as Z here, which need to satisfy this equation. Then conceptually, if we follow this trajectory, we can connect an image to a noise map. And usually, every single step in this trajectory is done by a neural network, so which could be very slow. So in one of our recent work, we try to address this problem by learning to do fast forward by a single neural network. So the core idea is very simple. We just try to set up another velocity field, which is conceptually the average velocity. So think about a starting point R and an ending point T. We can just set up the average velocity, which is just simply the integration between these two time steps divided by the time interval. So conceptually very simple. Then for some ending point in the middle, the velocity field will look like this. And if we move the ending point, the velocity field will change. And if we move the ending point to the entire end of the entire trajectory, it will look like this. Then conceptually, we can show that this average velocity field would be connected to the original velocity field by this equation. And this equation can provide us a principle to learn a neural network that can directly map between 2 points in this trajectory without solving the ordinary differential equation. So if we can do that, then conceptually, we can directly go from the starting point of the trajectory to the end point. This means we can sample a noise, and if we go back, we arrive at an image. So this is how we can do one-step generation using the latest generative models. So these are some of the images generated by this model, and they look pretty good. And if we zoom in into some of these examples, here I compare the results between solving the original ODE versus the fast forward done by the neural network. Actually, these two images are not the same. They look similar, but they are not the same. So they are similar at the high-level semantics. For example, both are the fish. Both are the fish of the same kind. They have a similar pose. They are under the sea. But if you look at their tails, their fins, and the background, they are different in some of the low-level nuance. So actually, these are the properties that we may desire for many other applications. That is, we want to be accurate at high level, at a macroscopic level, and we also want to tolerate some low-level and fine-level nuance. So this is what neural networks are really good at. Okay, now it's time to go back to the physics and scientific scenarios. So we have seen how some of the most effective image generative models are connected to some of the physics models. But the same idea can also be applied to some of these original physics problems. We want to solve an ODE equation, but we don't want to do it numerically. We want to learn a neural network to do that. So if we do that, we will have a generation counterpart of the simulation scenario. So here is just a very simple toy example to illustrate the concept. So on the left-hand side is the result of simulation, and on the right-hand side is a generative model, which can do fast forward. So it is worth notice that these two solutions are not the same. You can notice that they are different. All the particles are different. But the generative model can preserve some of the high-level and macro-level properties, so such as a wave in this case. So this is really a desired property. So then actually the success of the Gen AI models in computer vision, in image generation, can actually bring up many good opportunities. So first of all, it provides us some machine learning models that can model the data with probability. That means the model is not only able to produce one solution, it is also able to produce many possibilities, many modalities. So it also has the ability to guess what is the probability of each solution. And what's more, there is a very good, very desirable property. That is, these neural networks are very good at preserving and predicting the high level, the microscopic level, and sometimes the mesoscopic level attribute, such as if I want to generate an image, I want it to be a fish. So if I want to predict whether there will be a storm in 1 week, I just want to know there will be a storm. The model is able to tolerate some of the fine-level nuance. So it doesn't matter whether the fish has a fin or a tail in that exact same way. It doesn't matter what exactly the texture the fish is. So it's just like when I try to predict the weather, I don't need to know the exact temperature or humidity of a certain day or of a certain second. So this is really the power of neural networks and some of the latest generative models. So zooming out a little bit, today's most powerful neural network and Gen AI models are good at preserving the attributes of interest. And if we can make use of this property, we can turn some of the infeasible problems that may take a long time to simulate into some problems that are very tractable. And with that, this concludes my talk, and thank you for your attention.
Hello, thank you very much. My name's Phiala Shanahan, and I'm very happy to tell you a little bit about physical predictions from physical generative AI. So I'm a theoretical physicist, and so the problems I'm interested in are physics problems. How can we understand the physical systems that describe the structure of matter at the most fundamental level and the interactions of that matter? A perspective I want to leave you with is that a physical system is itself a generative model. So you can think about the collisions in a particle collider, for example, at the Large Hadron Collider at CERN, colliding particles, and the output of that generative model, if you like, is what we observe in the detectors after the collision. From a theory perspective, we can see the same thing if we look at the equations that describe the measurement of some quantum observable in nature. So here I'm interested in a quantum observable, f, and on the right-hand side of this equation, I can write that mathematically as an integral equation where I have a multi-dimensional variable, I apply f that describes my quantum observable to that variable, and I integrate with a known probability density inside my integrand. By known, I mean that that probability density is described by equations that I can write down that describe the structure of our universe. Now, a way of rewriting this in a sampling or Monte Carlo picture is to say that computing this quantum observable f really just looks like evaluating my function on samples that have been drawn with that probability distribution. So computing this boils down to a generative model generating samples according to a known probability density. So from this perspective, this leads us to physical generative AI. So that is approaches to generative AI that include guarantees of, for example, asymptotic exactness, that I will generate samples according to my exactly known probability distribution, that encode properties of my physical systems, such as symmetries and conservation laws, and as we saw in the previous talk, that exploit various features of physics to improve the generative AI models. So I'll mention Hamiltonian mechanics in particular. So asymptotic exactness is, in some sense, an unusual requirement for generative AI, so I'll belabor this point just slightly. What I'm interested in here are solving equations, right? And so there's only one thing that any sort of AI, generative or otherwise, can do for me, and that is solve the equations faster. Or perhaps, even more importantly, solve equations that I otherwise can't solve. But the requirement of exactness is still there at the fundamental level. If I'm solving an integral and the answer is 2, I had better get 2, no matter what I do to solve my equation. Right? So we require mathematical guarantees of exactness. There is no room for modeling, approximations, or any sort of uncertainty that we can't systematically improve or remove in the limit of, say, an infinite number of samples. So that means that we have to create scenarios where if the generative AI algorithm is poorly trained or not optimized at all, I'm still guaranteed to get the right answer. Presumably, it will be very slow. If it's well optimized, I'm still guaranteed to get the right answer, but it will be much more efficient, and that's really what enables us to do new science. We've had great success with this kind of provably exact generative AI in applications to, for example, lattice quantum field theory calculations in nuclear and particle physics. So this is starting from the equations that describe matter at the most fundamental level and solving them exactly using numerical approaches. One way of doing that is via flow models. You saw some examples of generative models mapping between probability distributions in the last talk. You can do a similar thing, and with certain requirements on those models, you can guarantee asymptotic exactness in mathematically rigorous ways. But there are challenges in applications like this that are not the same as those, for example, in image generation. So you can see a comparison here on the right-hand part of the slide from your perspective of quantum field generation compared to image generation. And what I'd like you to note is that not only do we have to guarantee asymptotically the probability distribution of my samples, which is quite different, right? An image is a good image or not on its own merits, but for me it's the distribution of all the samples that must be precisely right. But we have an extreme inversion of a typical data hierarchy. So in the quantum field generation example, we have something like 10 to the 12 degrees of freedom per sample, but I might have only 1 or 10,000 samples available. The ratio of those two numbers is extremely different to that in an image generation case, where I might have samples described by just millions or billions of numbers, but I might have many billions of samples of those images. So it's quite a different regime, which means that many of the applications to things like image generation can't apply in this context. Symmetries and conservation laws, again, look very different in these kinds of settings and need to be built into the generative models from the ground up. So in this same setting of applications to what's called lattice quantum field theory, so solving particle and nuclear physics from the ground up, you do see symmetries that have some analogs in the world of images, such as rotations and translations with boundary conditions in, for example, a four-dimensional space. But we have other much more complicated symmetries that must be respected by the models exactly. So one example of that is what's called gauge symmetry, where I'd like you to imagine a grid. In fact, it's a grid in 4 dimensions, so a hypercubic grid, where on every edge I have a matrix. And there is a symmetry transformation that will change a configuration which has the same matrix on every edge to one which has a different matrix on every edge. Every single edge is different, but those two are exactly the same from the physics perspective and must be generated with precisely the same probability. So deep internal symmetries that the generative AI algorithms have to respect. I won't tell you how you can achieve this. I can point you to references where this can be achieved. Okay, so the last point here on Hamiltonian mechanics, we can also leverage, as we heard in the previous talk, various properties, the structures of physical systems, to help develop new generative AI algorithms. For example, it's a fact that following some classical mechanics trajectory, so F equals ma, that we teach in 801, 809, 8223, you can in fact map out any probability distribution with the right momenta in the system. And so using these kinds of structures can help control numerical artifacts, it can help with scaling, and it has applications both in physics, where we have these various requirements and guarantees that we need to preserve, and in applications beyond. Okay, I've given you sort of just a tiny hint at how generative AI can be applied in the physical sciences. There's also a very good white paper written by colleagues in the NSF Institute for Artificial Intelligence and Fundamental Interactions that really maps out this virtuous cycle, this feedback loop that we also saw a little bit in the last talk, of the challenges presented by physical systems and physics problems that lead to new innovations in generative AI that then lead to new scientific discovery. And so we've seen this not just in my area of nuclear and particle physics, but across the physical sciences, that building generative models with various constraints and requirements and conditions and theory built in, so we can call that inductive biases, as well as important features such as uncertainty quantification, or in the case I talked about before, asymptotic guarantees of exactness, feeds back in to new generative architectures that lead to new discoveries both in the physical sciences and elsewhere. Okay, so the idea I want to leave you with is that physics problems like those I was discussing present both challenges and opportunities. They can be, in many ways, very different in nature from other generative applications. I had a comparison of, say, image generation compared to quantum field generation, where the hierarchy of data scales was extremely different, an extreme inverse. We have asymptotic guarantees of exactness that are required. We have complicated symmetries. But building all of that into generative models can lead you to new and more efficient architectures that then also have applications elsewhere. So this is the idea of physical generative AI, to achieve robustness, precision, interpretability, taking inspiration from the fact that physical systems are generative models, and so building generative models with the structures of those physical systems in is not only a natural way to study physical systems, but can have applications beyond. Thank you very much.
Hi. So we're going to switch gears a bit and talk about music. In my past life, I was a composer. I wrote for a lot of my friends, acoustic, chamber music, and then I started doing computer music. And then I realized, there was a lot of things creatively I wanted to do, but I felt like in terms of my engineering skills or my technological skills, I felt like I wasn't there to kind of like bring my vision and creative vision into realization. So I ended up doing a PhD in machine learning and also human-computer interaction. So today I'm gonna sound check. Awesome. So today I'm gonna talk about kind of my recent 8-year of an arc going from the lab to really bringing this technology into the concert hall. And what's really interesting about this process, it has been multiple years of me kind of finding my way, is it really kind of, in addition to thinking about music as modeling all the amazing structure, it makes us think more about human-AI interaction and what is needed to build systems that can can be partners in this co-creative process. So I'm going to start from 2017. Around June, the Transformer paper appeared on the archive. At the time, it was really, really impressive, but there was still a lot of uncertainty about, oh, what could this be useful for, and how far can we bring it? I felt it was the perfect model for music because in music, we have a lot of self-reference. Within a piece, that's how we build the meaning. So I thought, okay, yeah, we have a chance here to really model that long-term structure. And how do people come into this picture is we wanted also to model the pianist's expressive interpretation of the piece. So all the micro dynamics and timing, we want to be able to model that. So that is, after a year of getting it to work, there was a lot of architectural changes we need to do to better align it to the kinds of multi-level structure that was in music. And yeah, when it started working, we were seeing it generate amazing structure. For example, here you see these like grayed out areas. So this is a sample generated from the model. It's able to take these motifs, this like broken lines, tremolo gesture, and repeat it and add variation and really build out an arc. So I'll play some of that. So this is going to be an animation where you see kind of in real time how the model is thinking and looking back as it's generating forward. So yeah, this was 2018. Fast forward to this past year, I've joined MIT, and I'm really excited to be both in the music department and in the engineering school. And this has really allowed us to work with musicians on a day-to-day level. So this past summer, we recruited 3 MIT jazz musicians, and it has been really, really phenomenal, and it's been a lot of fun. And I think there's this unique situation where these musicians are also very technologically savvy and curious. So we were able to do a summer-long of co-design session with them to really take these systems and see how we can bring it into the concert hall. And of course, there's a lot of challenges. So previously, Lancelot and Perry from the Media Lab, we worked on the system that, in collaboration with a Grammy-winning keyboardist, very virtuosic, to think about, yeah, how do you make this happen? How do you go from a language model to an agent, a jam bot, that the musician feels like they have some kind of agency and partnership over in this live setting? So some of the things we had to do is think about, this is improvisation, so we're all kind of like improvising on the fly. And what kind of coordination needs to happen in order to make this duet work? There's different relationships. For example, I can play something and then you play something, or we want to be playing together. Yeah, in music a lot is like, oh, I'm playing different parts in the piece. And of course, this took a lot of system and engineering design to get the systems to be embedded in this kind of real-time setting. It had to be able to listen, it had to be able to prompt and schedule everything that was happening seamlessly on stage. So here I'll play you one of the early kind of encounters we had. And you can kind of see like how these models are still kind of trained on piano music where you tend to play in the middle of the piano. So you're kind of like fighting for space a little bit. So we'll see it. So this was our summer, yeah, kind of doing this every week.
I have no pedal for it.
Yeah, the model doesn't know how to pedal, so naturally the piano is sitting in front of the piano pedals for the model. Okay, so you kind of see they're trying to trade and trying to kind of make space for each other. And then later on, a couple minutes later, the musician kind of found maybe a local optima in terms of how to interact with the model. So let's see it. Thank you. So notice that the pianist in this local kind of optima setting ended up just using one hand because the jam bot was taking kind of the role of the other things that are happening. So if we wanted to do kind of a 3-hand piano, or a 4-hand piano, how do we do that? So some of the things we tried on the fly is, what if we gave the pianist more controls? For example, it could tell the jam bot which part of the piano they want the jam bot to be playing, or what kind of rhythm. And at the same time, we want this to be kind of a two-way conversation, like a two-way kind of communication. So the musician's communicating something, and then we want the model to also let the musician know, okay, yes, I'm going to be playing around here, and this is kind of the density of what I'm going to be playing. So I'm going to play you this last clip. It just happened 2 Fridays ago, where we had this jam bot in concert. And this is the musician, Andrew Lee. I'll stop there. Thank you all for listening.